Alright, so in this example, we had started off by making guesses about what certain selected response values might be, particularly the moment value and a little few of the reaction kind of values along the way here, and also the deflected shape. We didn't do a whole lot more, not as much as what we could have done in terms of guessing the shape of the moment diagram and that sort of thing. But we focused on this elastic deflected shape. We made this little mistake in here. We guessed that the rotation at B would be counterclockwise. That sort of was intuitive given the load situations, but we do have twice the stiffness in the left span as compared to the right. Now along the way we guessed that somehow the moment that we'd end up with would be somewhere between WL squared over 24 and 36, and that the reaction here in the middle would be about 7/16 of the total load. All right, we'll see how close we came to all that. Along the way we were assuming that, well, what if we inserted a hinge in the middle? That made this a prop cantilever. That's how we got some of these values in one bound. And then we said, well, what if it was fixed? We didn't really think that was reflective of reality, because this right hand span was actually more flexible than the beam that was being loaded. So we thought it would be closer maybe to this situation up here up front. Right, so let's check out what we found out. One, we found out in step 4 that indeed the rotation of B was a negative value. That's negative is opposite of positive, and positive is clockwise. So therefore the joint rotates counterclockwise. Indeed, that's what happened. We also found out that that moment at the B end of member AB was WL squared over 36. Well, look at that. That was one of our guesses as a bound, that somehow we thought maybe it would be between these two values, and it turned out to be WL squared over 36. Right, so that's kind of interesting. We drew the shear and moment diagram, and the shear tells us that the reaction at the left was 7/12 of WL. Right, so that's a little more than half, and that's in between. That's about halfway between the 5/8 and the 1/2 value. So that's interesting. And given that the moment was halfway between the two, I guess that maybe kind of makes sense. We guessed that the middle reaction, at least coming from the left, was 3/8 versus 1/2, and we didn't really talk too much about it, but we said maybe it's 7/16. Well, it turned out to be 5/8, which is a lot more than the 7/16. So, percentage-wise, right, that's more than half. This one, we were guessing less than half. Where did we make the mistake? And it all comes from, in our model, we assumed that the reaction at B was going to be entirely caused by what's going on here, and when we relax this a little bit and try to go in the middle, we didn't include what was going to happen with the curvatures of the bending, that is, from the right-hand span. And that right-hand span created some shears that added to the reaction at the middle. That's what we were missing when we guessed that particular reaction. So that's kind of interesting that tributary area really doesn't get us a good job at all, depending on what you consider to be a good job. I guess it would get us half of the total load would move over, and we're slightly more than that. So maybe it's not so bad, but on the other hand, it doesn't really, tributary modeling doesn't really reflect what's going on in the real beam very well at all in this particular case. Right? So what this tells me is that this kind of approach was not too bad. What we need to do to modify it was, when we went to this other fixed end case, we needed to draw this other right hand span and reflect this moment on over and say, okay, now what would happen with the shears that would go along with it? Had we done that, we would have gotten a much better value for BY. And again, we could have played maybe a halvesies games in between there and probably come up pretty close.